Hi guys, Essex Electrical Training here. We're doing a series of films on inspection and testing. This is the first one, and really I've got to make a bit of a, not excuse, but an explanation about myself, I suppose. I was an indentured apprentice in 1975. Came out of time in 1979. So I've seen a lot of changes, especially in relation to inspection and testing. So really, this series of videos, I mean, I could stand here, oh, welcome to the world of testing. I'm not one of them, okay? You don't need one of them, do you? I'm not one of them. But there are videos on, you know, wherever, and you're welcome to have a look. And I'm not, you know, knocking them down. They're fine. They go into it into the nth degree. But I'll take a sort of very pragmatic approach. So if you look at our series of videos and then look at their series of videos, and if you're somewhere in between, I reckon you'll be all right, okay? So, as I say, I've been doing it a long time. It's difficult for someone like me. There's not many sparks my age out there now. But what it is we did jobs, and the regulations were vastly different to what they are now. But anyway, we did jobs. I've been doing it for 48 years, and then, you know, you have to join these organisations, NICIC, NAPIT, and all the rest. And to people my age, it's like, well, hold on a minute. We've been doing jobs. I'm talking about jobs that we've put in ourselves, and nothing's gone wrong. Everything's okay. Yeah, I need to pay you £1,000 a year, join your organisation, so you can say, oh yeah, your jobs are okay. So it's a bit difficult, but that's the system. That's what it is. And that's what we do, okay? So there we are. But as I say, if you go to one of these bods, you know, able to, we've all worked with them, where they're able to quote every regulation in the book, and oh my God, do you want to be one of them? No, just want to get the job done. And I was unfortunately, fortunately, shouldn't say that, as part of the job is inspection and testing. So we've got to do it. But it's not the be all and end all. The job is the be all and end all. That's you know, getting the job done. But anyway, there we are, inspection and testing. So what we've got to do is look at it. I think whenever we're talking about anything really, is go back to the basics and how it all started, how it all came about. Before the war, I'm talking about domestic installations now. Okay, domestic installations. Commercial installations, even today, they sort of lead the field, and the domestic world follows. All the developments are in commercial. So, you know, from an early time, that they had power circuits in commercial buildings, and it was usually really rooms. They split it up into rooms, but it's be the lighting and power in one room on one circuit, because that's what it was in domestic as well. In domestic, you had a lighting circuit. That was it. You didn't have power circuits before the war. You had the cable that fed the lighting was slightly heavier than we use now, Imperial, and every appliance plugged into the lights. So if you had an electric kettle, it plugged into the lights. If you had an iron, plugged into lights. Electric fires plugged into lights. And that was the nature of installations in those days as well. There were fewer points, but those points carried or drew more current than we do now. Now we have multiple points, but drawing sort of less current. And you know, if we have a washing machine that draws 2.5 kilowatts, go, oh my God, we freak out. But anyway, there we are. I'm not getting into that. So it was really lighting. Now the trouble with lighting is it is picking up line and neutral. There is no earth in a lamp holder. That's what they used to plug into. There's no earth in there. It's just line and neutral. So if you had something that was class 1, that was metal and housed an element, then the potential for danger existed. If the element came into contact with the metal case would be live. More easily explained on this little mock-up that we've got. So here we have it. Let's say that this is a boiler, okay? So there's an element in there, and it heats water or whatever, and there it is in a metal case. So in those days where you plug it into the lights, you had a line coming in, going around the element and going back on the neutral. And obviously, if this happened, and let's say that was the element working A-OK, but obviously elements break down. So if we had this that happened, there, you can see there's a break in the element there, and it's made direct contact with the outside, with that metal case. So now, that metal case is live. Someone coming along could turn around and go, oh, and touch the metal case and get an electric shock because they form the path to Earth. So how did we solve that problem? Well, what we did is we decided to add another cable, and we called it an earth wire in those days. So not a CPC, but anyway, there we are. It's an earth wire. It was on there. Let's attach the earth wire to that. Must be too cack-handed. I've gone with Blue Peter. Right, that's it. So we attach the earth wire there, and we know that now there's a connection between the earth. That is connected to Earth. And what we did is we made sure that the earth wire had a really, really low resistance, so that when the element went faulty and it came into contact with the metal case is connected to Earth, the earth wire had a really, really low resistance. Low resistance, high current. So therefore there'd be nothing opposing. There, the element is in opposition to the current flow. Here, if it touches here, we kept that really low. So there was nothing in opposition to the current flow. So the current increased massively. It shot down the CPC or the earth wire. It's got to get its current from somewhere. It can't manufacture it in the actual appliance itself. So what it did, it dragged it along the line. So under fault conditions, touches Earth, shoots down the earth wire, drags it up the line, shoots down R2, drags it up R1. That's why when you test R1, R2, because they're the two cables that are involved in the fault process, if you like. So then what we did also, we said, right, okay, we'll put a deliberate weak point in the line so that when it shoots down a CPC, drags it up the line, the current will increase massively. We'll make this deliberate weak point, say, a lead wire that can carry current, and it will be thin enough that it can take 15 amps, for instance, quite happily. But under fault conditions, the current increases massively, so therefore the current going through that fuse wire increases massively, the fuse wire melts, and if that's melted, then it's disconnected the circuit. It used to be called Earth equipotential bonding with automatic disconnection of supply. Earth A.D.S. Then they changed it to E-BADS, then they changed it to A.D.S. Now it's just A.D.S. Automatic disconnection of supply. That is what this process is. So, further, what happens is if this box, let's say that this box is this box, okay, so it's still got the element in it, it's this box, but let's say that it's sitting on a metal tabletop. This whole table is metal, it's metal top. Then what will happen is, shut that away. What will happen is that the fault on this metal box will transfer to the metal tabletop. So if you said to someone, oh, watch it, there's an appliance here with a fault on it, you go, oh, I'm not going to touch that. I wonder what's wrong with it. You'd think nothing of touching the metal tabletop, but it has transferred. The fault has transferred to the metal tabletop. So what did we do as Brits? And we had the empire then, so everybody else sort of followed us. We said, what we'll do is we'll attach another earth wire. This time we'll attach it to the metal tabletop so that if the current comes into contact with the metal tabletop, and this, for instance, for some reason has fouled, and you've got the line cable touching directly the metal tabletop, for instance, then the same thing will happen. It will shoot down the earth wire that is connected to the metal tabletop. It will drag it up the line of whatever's feeding it, and massive current, same thing will happen. Overcome the deliberate weak point and melt the fuse. So basically what that leaves us is inside the First word, equipotential zone. The equipotential zone is the house, is the office, is the factory. It's anywhere where there's electrical equipment or electrical circuitry. Then everywhere inside the equipotential zone would be at the same potential. So if you say, let's take it for instance, if you get a plug top with a lead on it, there we are. There's a lead on it, and you've got nothing on the end of the lead. You've got the 3 wires there, if you like. You've got brown, which is line, or black in the United States. You've got blue, which is neutral, and you've got green, yellow. So there I am. I'm going to plug it in. I'm going to do the super dangerous thing. I'm going to switch it on. There we are. So there's the 3 wires. So I can grab hold of the earth. Nothing's going to happen there. I can grab hold of the neutral. Nothing's going to happen there because it's not in circuit. I don't recommend you do this, by the way. But anyway, but the live cable, theoretically, if I went to anywhere in the house, if I touched it on the tap, if I touched it on the radiator, if I touched it on the immersionator, or if I had a big metal tabletop like in a commercial kitchen, if I touched it on there, then it would still have a path to earth. There'd be a low resistance. It would drag the fault current up the flex at the line that I'm holding. It would shoot down to earth, and the deliberate weak point would be the little plug top fuse in the plug, and that would be overwhelmed with current and disconnect. Automatic disconnection of supply. So that's what we had. Now there's refinements on that, obviously, but let's talk about power first. So after the war, they started putting in separate power circuits. Now they had a problem. How do we put these separate power circuits in? Well, number one, they didn't at that time. I know it sounds incredible at the moment, but they didn't think of putting the earth cable. Let's say we're taking a bit of, twin and earth here. There's a bit of twin and earth. They didn't think of putting the CPC or the earth wire inside the cable. I thought, oh no, that don't make any sense. Because they didn't have PVC, so cables weren't flexible. They couldn't make the cable out of copper, so it wouldn't be flexible. Also, there was a shortage of copper after the war, but guess what? For all those shells that we didn't fire, there was not a shortage of lead. So the first cables that you might come across were lead covered. They're still twin on the inside, but it had a lead sheath, and that was the CPC or the earth wire, whatever you want to call it. To this day, I mean, if you go into a house and there'd be some old houses where the lighting it's not the heavier cable, but it's twin. There was no requirement to have an earth at every point until 1966. So if you see a house that's twin, it was wired before 1966. So the power, we had a problem. So we had lead, and we had, remember, few points, but they took more current. So that's why they came up with the ring final. The ring final circuit came into regulation 1946. There are, I think, Singapore, Saudi Arabia, obviously, I think the Falklands, and there's a couple of others that use the ring final circuit. No other country in the world does, okay? They can't understand how the Brits use such a dangerous thing, which I'll come on to ring finals later. But there we are. That's the simple mock-up, and that is A.D.S. The further refinement. Okay, so let's look at that. What I've said is that when this goes 40, the current shoots down the earth wire, drags it up the line, and melts that deliberate weak point. So as electricians, what we say is, well, we don't want faults, obviously. But when we do get a fault, we want it to be a bloody good one. Loads of current flowing in a short space of time, so that disconnects, bang, in a very, very short space of time. But let's look at this earth wire. This earth wire, where does it go? Well, it goes back to the board or the consumer unit. In the consumer unit, it's connected to the main earth terminal. And in the main earth terminal, there's every other earth from every other circuit. There's bonding that goes to our metal tabletop, or our water pipes, or our gas pipes, or our oil pipes, or any fixed metalwork that you think needs an earth. So they're all connected. So when this goes 40, temporarily, until that disconnects, there's a rise in potential. You can't have current without voltage. There's a rise in potential on the whole, all of the metalwork inside the equipotential zone. So let's say that we wanted to keep that to a safe voltage. Now, as I've said before, the Americans, they reduced their voltage down to 120 volts. They was used to killing people deliberately, so they didn't want to kill them accidentally using electricity. But we won't mention that. So they reduced it to 120. But let's say we want to reduce it to a really safe voltage. The lowest voltage that's been known to kill anyone is 50 volts at half an amp. Okay, so 50 volts is really safe. 50 volts is called touch voltage. Touch voltage. So basically, that's what we want to keep it down to. So how do we keep this rising potential that's going to happen everywhere in the house, inside the equipotential zone? We adopt something that works on a different principle to A.D.S. We call them RCDs, residual current devices, and RCBOs. The Americans call them power disruptors, okay? I've worked in a state, so I know. Anyway, so what we did is they work on a different principle. So let's imagine, let's paint a picture of how they do work. Michael Faraday is known as the father of everything we know, a brilliant man who invented loads of things. But he said that if magnetism produces electricity, then electricity will produce magnetism. It's absolutely unavoidable. So what happens is, where there is a current flowing through a cable, then there will be a magnetic flux around that cable. It's unavoidable. So that magnetic flux is like a jelly that you can't see. It's invisible, you can't smell it, but it's around every current carrying cable. So let's take that cable. What we do is then we wrap it around an iron core, a polo mint if you like, wrap it around an iron core and then take it to the load. Then the load goes through an element, then it comes back on the neutral, and that neutral will also wrap around the iron core and then carry on. So what will happen is the current will go around, it will induce an EMF into the iron core, go off to the element, come back on the neutral, and that current will also induce an EMF into the element that is opposing it. They're going in different directions. Even with AC, they're going in different directions. And they basically cancel each other out. But if the line goes off somewhere and doesn't come back on the neutral, then there'd be an imbalance. There'd be an imbalance in that RCD. If the neutral goes off somewhere and doesn't come back on the line, then there'd be an imbalance in the currents. So on that polo mint, the iron core, there's also another coil called a trip coil. That picks up the difference, if you like, and then operates the RCD and disconnects it. So it works on a much, much lower current. It's much, much safer than the time it takes for A.D.S. to work. It's a different principle. It's called, so if we've got A.D.S, automatic disconnection on supply, then what we can do is we can add an RCD for additional protection to stop this rise in potential. So it disconnected everything beforehand. That's it